ready when you're ready.
All right. Well, thank you all for coming. My name's Dallin Penny. I recently defended my PhD from UCSB back in, well, it's been February. Has nothing to do with this, actually. This is a completely separate thing that I worked on this last year as part of the Pipelines program. So the Pipelines program was a program through the Navy and through UCSB where they gave interns from community colleges an opportunity to work on projects in engineering and science through NAVC and NAVFAC down at Point Magoo. And I wanted to get involved as a mentor because I went to community college. I went to the community college here. I went to the community college in Fresno. And so it's really important to me to give back to that program. So that's why I got involved. And then all this is from that program and what I kind of helped to do there. So the title of my talk today is Electrical Capacitance Tomography for Corrosion Detection. So like I said, last summer at the NAVC at Port Hueneme, we hosted community college interns, and I was given mentorship of two different teams. One of the teams was given the task of trying to detect corrosion within a naval ship environment robotically. So they had a little robotic platform, and they wanted to try to detect corrosion occurring underneath the paint on the walls and the bulkheads of the ships there. And they looked into a couple different ways of doing that non-destructively. One of them was using thermal sensing. The other one was just trying to detect corrosion with conductivity probes poking into the wall. And then the thing that I suggested was capacitance tomography, or just using capacitance as a way to detect corrosion. And this will kind of go into how that all works. So a capacitor in its simplest form is just two conducting plates separated by some distance d here. I think this is, some distance d here. So this separates these two conductive plates, so you have a charge on either one. So the capacitance is equal to the area, or it's proportional to the area of those plates divided by their distance separating them. And this capacitance signal is linear to either of these variables here. And if you have some kind of dielectric material or non-conductive material in between here, that also increases the capacitance, this K term here. So that's kind of what we want to try to sense is this K, but you can't really use this to interrogate a flat surface. So what you can do is you can open it up, and that allows you to then put something here that will change that signal based on that K value. So if you introduce some kind of dielectric material, that will introduce a change in the signal, the capacitance between these two plates. And the problem here is that this is now a nonlinear region of interrogation. And since this is an electric field between these two plates, it's really hard to tell, okay, is it here? Is it here? Where is that dielectric material in between these two plates? So this is like a wall. We can hold it up to the wall and we can try to see if there's corrosion there. So the metal oxides that form the corrosion comprise of a lot of different things, and what we were looking at was mostly iron oxides. So there's a lot of ferric metals that are used in ship construction, and it can be anything from hydroxides to oxides, and they have different dielectric strengths ranging from 2.5 to 20. But the background is very low, so it should be easy to detect any of those things compared to either the paint or the metal beneath it. So in order to sense a larger area, you can pair up the electrodes and make a big array of them. And using the array, you can spatially locate the corrosion on a flat surface. So instead of just having a pair where you have to scan it, across the whole thing, you can then just hold up the array, and then you can tell based on the capacitance between the pairs of electrodes, you can spatially locate the corrosion. So this brings me to the whole principle behind the sensing using the array of electrodes, and that's electrical capacitance tomography. And it's been around since, I think, the 70s, and it's a non-invasive dielectric permittivity imaging technique. There are different sensor architectures, so the one I just showed is considered a planar architecture. Most often in industrial settings, they'll use this for process flow control, and so they'll have a ring of electrodes sitting around a pipe. And then you can actually get an image of the inside of the pipe using those electrodes. In order to use this technique, it requires mathematical solutions to what are called the forward and inverse problems of ECT. The forward problem is a calculation to relate the nonlinear response of all of the sensing elements, all of the electrodes, to the actual permittivity changes within the sensing area. And then the inverse problem is trying to reconstruct that true permittivity sensing area image from a very sparse nonlinear capacitance measurement data set. So on the one hand, you have to try to model your whole system and try to calculate, okay, what's the actual response that you would see given, this amount of dielectric material and this area of the sensor, and then using that calculation, try to then reverse the process and measure things and try to reconstruct the image. So the first part is solving the forward problem. So what kind of a priori information is needed? You need to know what the sensor geometry is, if it's flat, if it's circular. You need to know all this because you're doing what's called a finite element solver usually to solve these problems. So everything is discretized into small little chunks, and you need to know exactly what your sensor sensing domain is going to be. You need to know how you're going to be measuring, so you need to know which electrodes you're measuring from. You need to know the number of measurements, and that's given by the total number of electrodes times n-1 divided by 2. That's the number of unique pairs between, say, 9 electrodes. You can get 36 unique pairings between them. And then you need to decide, okay, once I have these 36 measurements, what's the actual number of pixels I want in my image? You want to keep it as small as possible because you're taking 36 data points and trying to make 2,500 data points. So you're going up an order of magnitude just with a 50 by 50 pixel image, which is, that big on the screen. So you tend to try to make this as small as possible. So this is the kind of model sensor for this presentation. It's a 9x9 sensor, a 3x3 electrode sensor. Each sensor is 10 millimeters across. And in order to use this sensor, you would measure capacitance between each pair. So you'd usually apply a voltage to one of these, and then you'd sense the capacitance between each electrode and that excited electrode. So you do 7.8, 7.9, 7.4, 7.5, 7.6, and then you turn off that electrode, turn on 8, and do the same thing. Measure the capacitance between that and all the other ones, and you just keep going down until you've made your 36 measurements. So like I said, each measurement represents a unique pairing between an excitation electrode and a measurement electrode. So we've labeled this I, and the measurement electrode is J. So that's, like I said, 1, 2, 1, 3, all the way up to 1, 9. And so on until 8, 9. So like I said, this is all of the sensors have a nonlinear response to the presence of dielectric materials. So in order to actually solve this problem, we have to linearize and also discretize it. So we have to chop up our sensing domain into little discrete chunks or pixels. And we also have to assume that the response between each pair is going to be a linear to the amount of actual permittivity material between those electrodes. So this is a pretty gross simplification of this problem. There are a lot of higher order terms to this equation that we're just going to ignore, and you kind of have to in order to make this, a tractable problem. So this is a matrix equation where G is our image vector. This is our 2500 pixel image vector. Lambda is our 36 row matrix of capacitance measurements, and G is our column matrix of pixel values, and S is a Jacobian matrix which relates the two. So it's a m by n dimensional matrix, and this is basically like a relational matrix which allows you to convert between the two. And S is what we're trying to find. So we can say we have lambda, we have G, and in order to solve the forward problem, you have to find S. So in kind of simplified matrix form, this is what the equation looks like. Any questions so far? It's a lot of linear algebra. Not the most exciting thing. So we can solve all of those Sij values by solving these equations. So we solve this equation for each set of electrodes to produce all of our pixel value S, or to produce all of our S matrix elements. So we take the dot product of the electric field between any two excitement and sensing electrodes divided by the voltage applied to the electrode, and we just sum over all of the space that is of interest for that particular pixel. And to find the electric field, you take the gradient or the derivative in 3 dimensions for the electric potential. And the electric potential is found by using the Poisson equation. So this is a partial differential equation with boundary conditions. You can only really solve this on a computer. And so we have to use I use Mathematica, which is a programming language that's really useful for solving these kinds of things, makes it really intuitive, really easy. And it allows you to do finite element methods as well. So this is an example of an electrode here at the bottom, and then this set to some voltage, and then this whole side is set to 0 voltage, and this shows the electric potential between the intervening space between the two electrodes by solving this equation here. So we need to model the 3D space that we want to actually sense in, and we can kind of chop it up into little tiny pieces. So this is a mesh of the region. This is just, kind of a box with the sensor on the bottom. So we define the mesh region. We set our boundary conditions so that the voltage is applied to each of the 9 electrodes. And then Mathematica will loop through each set of boundary conditions and solves the electric field inside of this area 9 times. So this is a 2D plot of those 3. So these are slices right in the middle of that. So this is just taking a slice of this center area along this plane, and then plotting the electric potential for each of the 9 electrodes. So this is the electrode with I think this is 1.2 volts applied to it, and all the other ones are set to 0. So you can see how that looks right in the middle of the sensing domain here. So we then have to actually solve for all the S matrices, S matrix elements. So we take the dot product of all of those electric fields and sum over all of our pixels, And this shows the height map of where the sensitivity is greatest. So you can see that in between pairs of electrodes, you have much higher sensitivity versus just over the individual electrodes. And that kind of makes sense because, you know, you think about opening up the capacitor, you've made a capacitor with a tiny little area on one side. So the electric field is going to be strongest right in between them, and that's where you're going to have the highest amount of sensitivity for detecting things. So we need to simulate some kind of corrosion in order to test this matrix. So this is just a image. So this is a collection of pixels representing values from 0 to 1, and 1 here being the center of the dot, and then it just kind of gradually fades out to the background. And this just kind of simulates a spot of corrosion on any part of the imaging area. So this is called a phantom. And like I said, it can vary in size and location. So we've solved the forward problem. We've calculated all of these S matrix elements. We can then actually take that matrix, do the dot product between it and this phantom, and we can simulate actual capacitance measurements that you'd see between the individual electrodes. So this is the 36 different pairs of electrodes simulating what the actual capacitance would be if you were to have this spot of corrosion sitting at that particular spot on top of the electrodes. So this is kind of the first part of the problem is solved, forward problem, and now we need to try to do the inverse. So how do we take 36 actual measurements from a piece of hardware, an actual sensor, and convert that into an image that faithfully reconstructs what the actual permittivity distribution looks like? So there's a couple different ways to do it. The simplest and the fastest way is to do what's called a linear back projection. And that's where you just take the transpose of your S matrix and you take the dot product of the transpose with your capacitance measurements to approximate your image vector. So as you can see, there's a lot of imaging artifacts here. The size is not accurately captured, and you can see that there's artifacts from the matrix itself showing where there's a higher level of sensitivity between the electrodes here. So this would kind of tell you where the corrosion's at on the surface, but it doesn't really tell you how much you have, or, you know, it could be fooled pretty easily by a lot of different things. So not the best approach. A better approach is to do what's called least squares regression. And what you do is you take this value here, so you have some G that you try, and then you calculate this value and you try to minimize this value as much as possible. So you loop through a bunch of G vectors trying to approximate the true G until you get to some minimum value for this that you can set. And that is a little bit slower than linear back projection, but it can get you a little bit better picture. So now we're getting less artifacts. We're still getting a little bit of artifact here, but the spot is a little bit more localized. It's a little bit more true to what the actual size is, but still not quite there. We can also introduce regularization through ridge regression. So we can add a parameter here, alpha, and what this does is that it takes away some of the sensitivities between the really sensitive electrodes and kind of lowers them while increasing the sensitivity of others. This introduces some more kind of weird artifacts here, but it much better approximates the true size of the spot and its actual position on the sensor. So there are a ton more reconstruction algorithms out there that have been around for a really long time. Those were just 3 of them. There's a lot of iterative methods. And the problem being, like I said, is that there's very few data points that you have to work with to try to reconstruct an image. So the reconstruction is termed ill-posed and ill-conditioned, and thus it's very sensitive to noise. So there's a lot of traditional algorithms, and recently there's been a lot of work into using machine learning algorithms to improve this. And I've seen a lot of papers do this where they've been able to get pretty accurate reconstructions using machine learning. So in terms of actual implementation for the pipelines program, we never actually got to that point. By the time I had solved the forward problem, we'd already been 3 weeks into the program, and they were already ordering parts. And I was like, this is still an interesting thing that I want to like keep looking at on my own. So I ended up designing my own capacitance measurement circuit. Never actually got it to work. They ended up choosing thermography as the actual sensing technique to detect corrosion. But like I said, I did continue to try to develop it on my own. Yeah, Mathematica is only so useful. So mostly I just wanted to show the ideas behind electrical capacitance tomography, and the technique, what goes into actually using it, the math behind it, and that Mathematica is a pretty useful tool to do that. The commercial product actually already exists, and I didn't know that going into this. But someone makes, ASP Laser Incorporated makes this thing that you can, I think it kind of rolls along the floor, and then it uses a capacitance sensor to detect corrosion beneath paint. And that's all I've got. Any questions? Yeah.
So this is probably a naive question, but there's an answer to. But what's the, I guess, is there any technical issue with increasing the resolution of your sensor array just by adding more, like, more smaller capacitors, say? Because that'll, I guess, increase the ratio of your sensors to pixels, right? So
yeah. So that just becomes like a data handling and hardware issue.
Okay.
So you need a channel for each every individual electrode, and they all need coax cables.
Okay.
So it's like it gets very like cumbersome very quickly if you want to have a whole bunch of electrodes in an array. You can do it, and your noise also goes up pretty quickly with how small your electrode is. So there's kind of a lower bound on the size as well. So you don't want super small electrodes because then you're just getting mostly noise in all your measurements. So yeah, trade-off. It's hard to do that and just, without in a simulation because yeah. So you can get, this was kind of like a rough calculation, and like there's a couple things that I glossed over, like the sensitivity matrix. I had to do a couple things to get it to actually produce a good image, and that might not work with a real sensor. So like I had to normalize a couple different things, and like because some of the terms were like -18 on the sensitivity matrix. So it's like you can either normalize it and get just like a noise image, or you can or not normalize it and get just a noisy image, or normalize it and get an actual image. So if this could actually work is an open question. It does work because people do it, but I don't know if my approach was the correct one.
I have a question here from Interwebs. What software did you use for PCBs?
I used Easy EDA. So it's an online platform that's free to use, and it's from JLC PCB. So they have the whole ecosystem where you design your PCB and then you can just hit order, and it's like $5 and it'll come straight from China. So yeah, really easy to use. Yes.
I feel like the way I feel like StudFinder works the way your thing works. And I wonder if you could extend this to add a motion system to your electrode array to get an effective higher level.
Yeah, you probably could.
Sensitivity between the plates. So by moving the plates, you run the more sensitivity region over the test surface.
Yeah, yeah. If you had a way to track position really accurately, you could get a much better image because then you could kind of overlap all of the measurements over one area and kind of average them. So if you had a really good way of tracking position, like a motion encoder or something, you could probably get a pretty good image of the surface. If I had the resources and time, that was something I was hoping to do eventually. Any other questions? It's hot in here.
I have a question about the mathematics.
Yeah.
I haven't taken linear algebra or vector calculus in a while, but which part of that for the methodology is the actual linearization?
Let me go back here. So this equation has like an extra, this has extra terms to it.
Okay.
So there's like nonlinear terms that are squared, cubed, whatever. So those are all just kind of dropped and ignored. So yeah, and yeah, there's a couple different things there.
So we may have talked about this already, since this is my second time.
Yeah.
But was there ever any talk of follow-on to the program by Navy and also extending the team to larger surfaces?
No, they weren't super interested in this. Mostly because I didn't really communicate it very much to them. I was just kind of told them that I was working on it, and they were like, "Oh, that sounds cool." And then when they decided, because I was just there as a mentor, I wasn't there to make any decisions. So as soon as my team was like, "We're gonna go with the easier option," I was like, "All right."
I'm guessing the idea was Paul just analyze a slice look, right? And then
Yeah.
change it.
Yeah, yeah, yeah. Yeah, a couple of them were like they had their little robots, and like the whole time was just spent getting the robots to work. Like I don't even think they got the camera to work in the end. The little thermal camera that they bought. And they had like a budget of like $100 for each team. So yeah.
I'm not sure how they analyze the holes. Do they have to get them out off the water?
They're only interested in what they can actually like look at. So it's like stuff that's inside, or like stuff that's on, the outside that you can actually get to. So like what a robot could do is pretty limited compared to what a person could do. So it was like very limited environment.
Good question.
Yeah.
I don't know if you covered this, but did you actually talk about what the probe itself looks like? You said you had coaxials coming out.
Oh, yeah. So it's just so the sensor itself could just be made out of a PCB. So you could just have, copper areas arranged in a grid, and then have like coaxial connections coming off of there, the edge of the PCB board, and that would work as a sensor.
Is there a reason you didn't want to integrate the sensors in there to get rid of the capacitive loading of coax cables? Because I imagine the capacitance is pretty small here.
Yeah, this is like picofarad levels of capacitance, so it's very, very small signal. So if you can get away from using coaxial cables, it's definitely better. The problem is you run out of room because it's a pretty big PCB. It's like this big. So yeah, I'm sure someone who's better at making these things could probably figure it out, but yeah. Yeah, it's super, super small signals with these. Yeah.
Saw a bunch of stuff that looked like that circuit board and cables in that little bin over there.
Oh, you did.
Wound up.
That's exactly where they wound up. Yeah. I think they might still be in here somewhere.
Hands on my car.
Yeah. This is all our donations to the hackerspace when we moved. Any other questions? All right. Well, thank you. Appreciate you hearing me. All right. Just stop.